Hello everyone, welcome to the third episode of Weekly Math Hunter. Today, Shomik and I will discuss a topic on number theory. We would like to give a shout out to Stranger Chaudhary for providing us the correct answer from last week's challenge problem, and he will be considered for the Ramanujan Scholarship at Chinta. Please keep watching this video for the upcoming challenge problem.
Hello Rupkatha, I'm glad to be here today. So to discuss this topic on the number theory, we should set a motivational problem at first. The problem is we are given a natural number. We need to find all of the numbers which are less than n and co-prime to n.
Okay.
So tell me when two numbers are called co-prime.
When they do not have any common factor, that means the GCD is 1.
Okay, give me an example of two co-prime numbers.
5 and 7?
True. 5 and 7 are co-prime, but they are primes also. Can you give me such an example where the numbers itself are not prime, but they are co-prime to each other?
Yes, 4 and 9.
Yeah. So we see that two numbers to be co-prime, they need not to be prime itself. Okay. I'll give you an example. Let's say 12. Okay, which is a very easy number. Can you find all the natural numbers which are less than 12 and co-prime to 12?
Yes, I think 1, 5, 7 and 11.
True. So there are 4 such numbers which are co-prime to 12 and less than 12. But it was a pretty small number and we could count it manually. What if we are given a very big number? How can we count such the required numbers co-prime to that number? Let's say for n, co-prime to n and less than n. So our goal is to find that. And we will create a machine for that. Okay. Name of this machine, we call it phi. Phi is a machine which counts our required number for us. So as we have seen, if we give input of 12 in this phi function or phi machine, it will give it output of 4, right? Now can you tell me, if I give input of 11, what output I will get?
We will get, I think 10 numbers. It will count 1 to 10 all the numbers.
Yes, so it will count all the numbers 1 through 10 and we will get the output as 10. Okay, so now can you tell me that if we give input of any prime number, what kind of output we will get? For example, if the input is p, which is a prime number, what do you think the output will be?
All the numbers less than p are co-prime to p, so the output will be p minus 1, I think.
Correct. So output will be p minus 1. So now we know if we give any prime number as input, the output is going to be p minus 1. So for any prime number, the problem is solved. We can easily count that how many such required numbers are there. Let's talk about square of prime numbers. For example, 9, which is square of 3. So if 9 is the input in the phi function, so what do you think the outputs are?
The outputs are, I think, 1, 2, 4, 5, 7 and 8.
Correct. So how many of such numbers are there?
6 numbers.
6. So the output will be 6. So you see what you actually did, you have taken all the numbers from 1 to 9, but you have excluded the multiples of 3 because we know the multiples of 3 are never co-prime with 9. Exactly. So there are 9 numbers starting from 1 to 9, but 9 is the third multiple of 3 because it's 3 square, right? So it is the third multiple of 3. So we have to exclude 3 multiples. So from 9 we exclude 3 numbers, so there are 6 numbers.
Okay.
In general, if p square means a square of a prime, if that is input, what do you think the output will be?
P square minus p?
Exactly, it will be p square minus p because we have to take all numbers starting from 1 to p square, but we have to exclude the multiples of p, and we know that there are p multiples of p because p square itself is the pth multiple of p. Okay, so it will be p square minus p. Now we can understand by seeing the pattern that if the input is p cube, means cube of a prime, it will be the output will be p cube minus p square because again p cube is the p squared multiple of p. So continuing in the same manner, if we now take any power of a prime number, so now we are generalizing it further. We are taking any prime and any power of that prime. So let's assume p to the power k. So if p to the power k is the input, what will be the output? The output will be p to the power k minus p to the power k minus 1. Correct? I'll be writing this in a different form. If I take p to the power k common, this will look like p to the power k times 1 minus 1 over p1. So now we know that if we are given any power of a prime number, how to find phi of that number. Okay, so for example, 81 is 3 to the power 4. So this will be a challenge for our viewers to find out phi of 81. Our goal will be to get the absolute general form. Means if we are given any natural number, we will be able to find out phi of that natural number. But before we do that, we need to know about a property of functions which is called the multiplicative property of function. So let's say if f is a function, then if f satisfies the property that f of mn is equal to f of m times f of n, where m, n are inputs, then we call the function f is multiplicative. Phi also has this property. Phi is a function and phi also has this property, but there is a restriction that phi of mn will be equal to phi of m into phi of n, provided if m and n are co-prime numbers.
Okay.
Let us consider a list of natural numbers n1, n2 up to nk, where all of them are mutually co-prime. So what does that mean? That if I pick any two numbers, they will have the GCD
exactly
is equal to 1, right? Yeah, so now if I take the product of this n1, n2 up to nk, phi of this product I can write by using the previous property. I can write phi of n1 into n2 into nk, that is equal to phi of n1 into phi of n2 into phi of n3 and so on till phi of nk. Okay, let us consider a natural number n. Now, by fundamental theorem of arithmetic, any natural number can be, either it will be a prime itself or it can be expressed as a product of primes. Okay, so any natural number can actually be written as this form, which you can see on the screen. So it will be written as p1 to the power alpha 1, p2 to the power alpha 2, so on up to pk to the power alpha k, where each of these pi's are distinct prime numbers and alpha i's are their respective powers. Okay, now we want to find out phi of that natural number, right? So we know phi of n will be equal to phi of this big expression, p1 to the power alpha 1, p2 to the power alpha 2, so on up to pk to the power alpha k. Now you see that, notice this, p1 is a distinct prime, p2 is a different prime, all of them are different primes. So they should not have anything in common. So each of these factors here, like p1 to the power alpha 1, p2 to the power alpha 2, they all are mutually co-prime, right? So using the last property, the multiplicative property of phi, we can write that phi of n is equal to phi of p1 to the power alpha 1 times phi of p2 to the power alpha 2 times phi of p3 to the power alpha 3 and so on up to pk to the phi of pk to the power alpha k, right? Now we already know how to find out phi of any power of a prime, and these things are nothing but power of primes. So we can find out each of these factors individually and then we will obtain phi of n. So phi of p1 to the power alpha 1 will be p1 to the power alpha 1 times 1 minus 1 over p1. Similarly, p2 to the power alpha 2 times 1 minus 1 over p2 and so on up to pk to the power alpha k times 1 minus 1 over pk. Now, if I just take only these factors, p1 to the power alpha 1, p2 to the power alpha 2, so on up to pk to the power alpha k, I get back n, and the remaining factors remains as it is. So phi of n becomes n times of 1 minus 1 over p1 times 1 minus 1 over p2 and so on up to 1 minus 1 over pk. So this is the general form of phi n. Now if we are given any natural number n, we would be able to find out phi of that number. Means we would be able to count all such numbers which are co-prime to n and less than n, right? Okay. So now again there will be a challenge for our viewers. So I would like them to find out phi of a very big number, let's say 2700. So all of you please find phi of 2700.
Viewers, if you think you can answer the questions, please comment down below. You may be mentioned in our next video.
Till now, using the phi machine or phi function, we counted our required number. Means if we are given n, we counted all the numbers which are less than n and co-prime to n. But our actual goal is to find the sum of these numbers. Okay. So now we have to think a little bit differently. Let's say we are given n, and a1 is a number which is less than n and also co-prime to n. My claim is that n minus a1 that will also be such a number, means it will also be coprime to n, and it is definitely less than n. So this will be our third challenge for our viewers, to prove that if GCD of a1 and n is 1, means if they are coprime, then GCD of n and n minus a1 will also be 1. So I have a a1, and for that I have a pair n minus a1, right? I'll consider a few more numbers. I don't know how many such numbers will be there. So let me just consider that a1, a2, a3 up to ai numbers are there, which are our actually required numbers. Okay. So for each of them, I'll get a pair, right? Like as I got for a1 n minus a1, for a2 I'll get n minus a2, for a3 n minus a3, and so on till n minus ai. Okay. Now again I'll make a claim that none of these ai's are equal to n minus ai's for n greater than 2. Because if that happens, if ai is equal to n minus ai, then you can just do a little bit of simplification. You will get that ai is nothing but n by 2, right? Now think, what is n? N is a natural number, so it could either be even or it could be odd. So if it is even, then n by 2 even, and it is also something greater than 2. So n by 2 is also even, right? Isn't it?
Exactly.
So if we have two even numbers, they will have at least 2 in common. They cannot be coprime, right? Isn't it? So that, like, if ai is n by 2, it cannot be a coprime number. We are getting a contradiction there. Now if n is odd, then n by 2 is not even a natural number. It is like something in fraction, so it cannot be ai, right? So our claim is true that ai can never be equal to n minus ai if n is greater if n is greater than 2. Okay, if it's something more than 2. 2 is the only exception here. Okay, so that means this is a very good observation, that the numbers we are counting, they are always like the numbers which are coprime to n and less than n, they are always like, there are even number of such numbers. You see, if there are ai's, for each of them you will get a pair, right? So there are always even number of such numbers. Now think what this I equal to. I equal to what? Is it something known?
So these AIs and n minus AIs are all our required numbers. So it must be equals to phi n.
Correct. So there are two I numbers, like AIs, I numbers, and n minus AIs, I more numbers. So two I numbers, and as you said, they are definitely equal to phi n. So I must be equal to phi n over 2. So now we will add up all these AIs and n minus AIs. So let's take A1, then A2 plus A3, so on up to AI, and then n minus A1 plus n minus A2 up to n minus AI. Now I'll be taking these terms in pairs. I'll take A1 and with it I'll take n minus A1. With A2 I'll take n minus A2, and so on till AI and n minus AI. So now if you look that from the first pair, A1 and n minus A1, I'll get an n, right? From the next pair also I'll get an n. From each of these pairs I'll get an n. So how many n's I'll get?
I numbers of
Exactly, there will be I numbers of n. So the total sum is coming to be n plus n plus n up to I times, right? So the sum would be I times of n, in. And we already know what is I. I is phi n over 2, right? So the sum is coming to be n into phi n over 2. So if we are now given any number, any natural number, we can find out the sum of all numbers which are coprime to it and less than it using this formula.
Please do comment your answers for the questions raised by Shomik, and the best responders will be mentioned in our next video. If you find this video helpful, please like and share with your friends. For more such mathematical contents, please subscribe to our channel.
If you want to know more about our Math Olympiad, ISI, CMI and research programs, please log in to chinta.com.
Goodbye, see you in our next video.